Okay, good morning. So this is 40th lecture and we are studying the flow past immersed bodies and we have already talked about the flow past a flat plate. If we have a sharp flat plate and Reynolds number is small, then there will be thick boundary layer. On contrary, if our Reynolds number is high, then we will be having very thin boundary layer, and over the thin boundary layer there will be applicability of the boundary layer theory, which I told you in the previous class, that if there is a thin boundary layer, then I can calculate pressure outside the boundary layer in inviscid region, and that same I can apply within the boundary layer. Okay, and typically the boundary layer thickness, if we solve, then from the Blasius solution we will be getting delta by x equal to 5 by Reynolds number square root for laminar flow and 0.16 by Reynolds number 1 by 7 for turbulent flow. And you can see the comparison. If you have a smooth flat plate and the free stream flow is uniform, then transition occurs nearly at 3 into 10 to power 6 for this is the critical Reynolds number at which my flow transforms from laminar to turbulent flow. But this only happens if my profile is smooth, so flat plate is smooth, and also the free stream velocity is actually without any disturbance. Okay, on contrary, if I consider that my industrial flat plate is there, so industrial flat plate means that will be having certain roughness, and also in the practical scenarios there will not be any perfectly smooth free stream flow. Okay, so in the free stream also there can be small deviations in the direction of the velocity. Okay, so because of this, for practical scenarios, critical value of Reynolds number will be 5 into 10 to power 5, and in majority of our numerical problems and the practical flow conditions, we will be using the critical Reynolds number of 5 into 10 to power 5. Is this point clear? Please make this point very clear, that for smooth and idealized situations, the transition occurs at 3 into 10 to power 6 of Reynolds number from laminar to turbulent flow. But for practical scenarios where we are having rough plates and where we are having the slightly disturbed free streams, their critical Reynolds number will be from 5 into 10 to power 5. Okay. Then we can have other type of bodies which are called as actually the blunt bodies. And if we see in case of blunt bodies, in very ideal scenario, I can find the presence of this thick black dashed colored line, and this black colored line is nothing but representing the boundary layer thickness, and then I can have a very smooth wake, and we can have the other movement of the boundary layer streamlines outside the boundary layer region. So this type of condition is idealistic condition. If this type of condition can exist in the practical scenarios, then boundary layer theory will be applicable for these conditions as well. On contrary, we will be finding that in real life conditions, we will not be having this type of smooth profile, but because of the presence of adverse pressure gradient from this point to this point, because in this region whenever we are moving, our flow area is expanding in this direction. So as the flow area is expanding, here there will be decrease in velocity and increase in the pressure at the expense of the velocity. So because of this, we will be finding adverse pressure gradient, which will lead to the separation of the boundary layer from the body. And you can see in the downstream portion of the body, this is my boundary layer streamline. This is the outer streamline, like which can be considered as the boundary layer thickness, and within that I will be having lot of recirculations and highly disturbed wake profile. For these type of conditions, we cannot apply the boundary layer theory to find the solution of this type of system. Okay, so that's why uh, for the blunt bodies, if we consider the blunt bodies which are present in the flow, the majority of the solutions are either experimental or computational. There is no theoretical solution till date available for this type of situations. Okay, then one very famous equation comes, which is called as the momentum integral estimate, and momentum integral estimate is given by Karman. This was initially given for the approximate solution of the boundary layer flows. By using this momentum integral equation, what we can do is we can basically we can uh, have the approximation of the velocity profile and by using that velocity profile I can actually determine different boundary layer parameters. Okay, so typically to understand the momentum integral equation or how it can be derived, what we have done, we have considered a flat plate, and over this flat plate, say this is my boundary layer region, and outside this I have the inviscid region. Okay, now to understand this, what I have considered, I considered that this is my thin boundary layer, and say u infinite u naught is my free stream velocity, and I have some streamline outside the boundary layer which is starting at a distance of y equal to h, and this streamline is slightly deflecting along the flow and it is reaching a distance of y equal to delta at some at the trailing edge of the plate. And of course at the inlet x equal to 0 I will be having a smooth streamline, this kind of uniform free stream velocity. On contrary, at the trailing edge of the plate I will be having the variable velocity, where I have gradient of the velocity till y equal to delta, and after this point we have the constant velocity. Okay, now by taking the help of this analysis, one more parameter we are considering, that plate width we are considering v, which is normal to the board. Okay, by using this particular streamline as my control volume, so whatever the blue colored streamline I have shown over here, this I will be considering as the top face of the control volume. Then this side and this side are the left and right faces of the control volume, and this bottom wall is nothing but the bottom face of the control volume. Okay, so by using this particular control volume estimate, if I now apply the Reynolds transport theorem over here, then I can calculate how much drag force will be acting on this plate. So this is something which I have already discussed while we were talking about the Reynolds transport theorem, particularly in our fluid dynamics study. Okay, when viscous effects we were not actually considering. So if I apply the Reynolds transport theorem, then according to Reynolds transport theorem, sum of all the forces which are acting on this body, which is typically over here a drag force, and of course this drag force is acting in the negative direction, that's why I am writing it as a minus d, that will be equal to rate of change of momentum in the control volume. For steady flow situation, there will not be any change of momentum within the control volume as function of time. Okay, for steady flow situation, and for steady flow situation only change of momentum will be across the faces of the control volume. So one face of the control volume is bottom wall, and in bottom wall, because of the presence of the solid wall, it will be impermeable boundary, and I will not be having any vertical component of the velocity, which will be 0. Okay, similarly, what I have done, in the top portion of the control volume, I have not considered a fixed boundary, rather I considered a streamline outside the boundary layer region as the top portion of the control volume. Okay, so any velocity normal to this streamline will also be nearly equal to 0. So that's why I will not be having any momentum exchange in the bottom and the top face of this control volume. The only momentum change will be in the left and right side. Okay, so you can see the momentum change in left face, which is designated as face 1, that will be rho times integral 1 u into dA. And what is velocity? Velocity we have to consider as the normal component of the velocity, because rho u into dA is my mass, and normal component of the velocity will give me momentum. Similarly for phase number 3, so now this is the incoming momentum minus of outgoing momentum. So that way I am getting over here plus sign, and this is rho integral 3 at the phase 3 u times v dot n into dA. Is this point clear? So from this integration you can see that v dot n will be minus u naught for the first phase, because here this velocity is uniform u naught only, and this is into the plate. So into the plate means normal component is inward to the surface. So outward is considered positive, inward is considered negative. That's why it is minus u naught. And here In this case, my velocity is actually u, so that's why I have written over here plus u. Is this point clear? So by doing this, one more important thing I have done over here, while I have written this first term, I have used my limits of integration from 0 to h, because this streamline which is forming the top face of the control volume, it is varying from 0 to h in the phase 1. But in phase 2, it is varying from 0 to delta. So that's why I am writing it as 0 to delta while I am doing the integration of the third phase. Up to this point, is it clear? Okay. Now, I can further simplify this equation. In this first term, all these terms are constant. So, integration of dy will be simply over the h will be simply h. So, that's why I have written over here rho u infinity square b into h. And in the second case, because u is function of y, so I cannot take it out of integration. So, I need to know the functional form of u as function of y, then only I can integrate this. So, for the second case, what I have done, I have written it minus rho v integral 0 to delta u square into dy. Up to this point, is it clear? Okay. Now, what I am doing, in order to further simplify this equation, I am first writing the continuity equation. So, as per the continuity equation, density times integral over entire control surface v dot n dA will be equal to 0. This is nothing but my integral form of continuity equation. Now, this will give me, because there is no velocities in phase number 2 and 4, so only v dot n dA integral I need to calculate at phase number 1 and phase number 3. Okay. So, at phase number 1, it will be rho times integral 0 to h minus u naught, because v dot n is negative. So, minus u naught b dy plus integral 0 to delta u b into dy. Up to this point, is it clear? This has to be equal to 0. So, from here, one important conclusion we are getting, and that important conclusion is that this integration will be becoming u naught into h. Okay. That u naught into h is nothing but integral from 0 to delta u dy. Is this point clear? So, now what I will do, in my drag force formulation, my first term is u naught into h, and u naught into h is what? Integral 0 to delta u dy. Okay. So, that is what I have done over here. So, this rho u naught square bh, I have written rho u naught into h into u naught, and this u naught h I will be replacing with 0 to delta u dy. Okay. So, that is why my drag force will become 0 to b integral 0 to delta u times u naught minus u into dy. Is this point clear? All are clear with this idea? So, basically whatever I have calculated over here, when I have substituted in this particular point, then I got this formulation of the drag force. Okay. And one simple generalization theory. So, till now this control volume is still x equal to L. If I have to generalize this, then I can write delta at any arbitrary value of x, and then I will be writing this equation simply as u into u minus u dy. Okay. So, this particular equation, if boundary layer is present, then this equation can give you the value of the drag force present in the flow. Okay. So, by this equation actually, if I know the value of velocity profile, if I simply know the value of velocity profile, I can calculate the corresponding drag force. So, this is called as Karman's momentum integral equation. In this equation, if I simply substitute velocity profile, I can calculate drag force, I can calculate wall shear stress, I can calculate skin friction coefficient. Okay. Now, let's come for the Karman's analysis of the flat plate. Okay. So, in this analysis, what we are considering, once again the situation is identical, x equal to 0, x equal to L, At any arbitrary value of x, my delta will be a function of x, because boundary layer thickness is changing as we are changing our x. Okay, and this is the velocity profile, and within the boundary layer, and our wall shear stress will also be a function of x, because velocity is function of x, so that's why wall shear stress has also to be a function of x. Okay, now the previous equation which I have written over here, if in this equation I use one parameter theta, which is equal to integral 0 to delta u by capital U into 1 minus u by capital U dy. If my theta parameter is something which is momentum thickness, so just now I have derived you over the board the formulation of momentum thickness. So if I replace this second term with the momentum thickness, then I can write my drag force as nothing but rho b times u square into theta, where theta is equal to this, and theta is nothing but my momentum thickness. And what is momentum thickness and displacement thickness? I already introduced you, and I have given you the derivation over the board. Okay, is this point clear? So it means that I can write my drag force rho b u in u square times theta, where theta is nothing but u infinity. Okay, now drag force can also be written as, what is drag force? Drag force is nothing but the force which is acting parallel to the body, and parallel to the body we will be having certain stress that is causing this force. Okay, so the stress which is parallel to the body, that is nothing but my wall shear stress. So that's why I can also write the formulation of drag force as, this is width parameter integral 0 to x tau w x into x. All are clear with this idea? Okay, because wall shear stress will be function of x. So if I integrate it along the length of the plate, and if I multiply it with width, then ultimately what I will be getting nothing but my drag force. Okay, is this one clear? Now if I take derivative of this drag force as x, so derivative of this drag force with x will be b times, and this was the integral over the x, so this integral will vanish and it will simply become wall shear stress tau w. All are clear with this idea? Then similarly, if I take the derivative of this drag force which is coming from the momentum integral equation, okay, so if I take the derivative of the drag force which is coming from momentum integral equation, d by dx equal to rho b u square into d theta by dx, if I now equate these two, then ultimately I will be getting that my wall shear stress will be equal to rho u square into d theta by dx, where u is nothing but the free stream velocity at the approach point of the plate. Okay, all are clear with this idea? Now then comes important point. So what Karman has done for laminar boundary layer region, the flat velocity profile is approximated by using parabolic variation. Okay, so within the laminar region, velocity profile can be written as capital U times of 2y by delta minus y square by delta square. So this is nothing but the parabolic variation of the velocity profile within the laminar boundary layer region. Is this point clear? So within the laminar boundary layer region, I can assume the velocity profile to be parabolic. Now I have substituted this parabolic velocity profile into the formulation of momentum thickness, and from here I find that momentum thickness is nothing but 2 by 15 times of delta. Is this point clear? Momentum thickness is 2 by 15 times of delta. We also know that wall shear stress will be mu times del u by del y. Okay, wall shear stress can also be written as mu times del u by del y at y equal to 0 at the wall. So if I have this as the formulation of u, I can calculate the derivative of this u with y and calculate it at y equal to 0. If I do so, I will be getting that wall shear stress is nearly equal to 2 mu into capital U by delta. Is this point clear? So now, one wall shear stress I got 2 mu U by delta. Another wall shear stress I can write from the previous equation that tau W equal to rho U square into d theta by dx. So d theta by dx will become 2 by 15 into d delta by dx. Okay. So one wall shear stress equation I have got from the momentum integral equation, and another wall shear stress equation I have got from the velocity profile. Now I can equate both these wall shear stress equations. Is this one clear? So I can equate this equation to this equation. If I equate this and this equation, then I can do the separation of variables, and what I will be getting, that delta times d delta is nearly equal to 15 times nu by u into d. Is this one clear? So after doing the separation of variables and by comparing these two wall shear stress equations, I will be getting this equation. So now what I have done this integration. If I do this integration, then I will be getting 1 by 2 del square equal to 15 mu x by. So, and further simplification of this gives me that delta by x equal to 5.5 nu by ux power 1 by 2, which is equal to 5 by 5, 5.5 divided by Reynolds number at x power 1 by 2. Okay. So whatever this solution of delta by x we are getting, this is nothing but called as the approximate solution of boundary layer thickness. Why it is called as approximate solution? Because for calculating this solution, we have taken the approximation of the velocity profile. And what was the approximation of velocity profile? That our velocity profile is parabolic and it varies by using this particular formulation for laminar flow. Is this point clear? So that's why this is called as approximate solution of the boundary layer thickness. And by knowing this solution, if I calculate the Reynolds number corresponding to any value of x, it means in my definition of Reynolds number, if I consider x as the length scale parameter, then I can calculate the corresponding value of the boundary layer thickness. Is this point clear? Now, same can also be used for calculating the friction coefficient. This CF over here is called as skin friction coefficient. So the way we were having friction factor for internal flows. In case of internal flows, we were having one important parameter that we were calling as nothing but our friction factor. Similarly, over here we will be having one factor which we call as skin friction coefficient. And skin friction coefficient is nothing but wall shear stress can be written as skin friction coefficient times half rho u square. Okay, so this is the fundamental definition of wall shear stress in terms of skin friction coefficient. So then from here skin friction coefficient will become 2 tau w by rho u square. Okay, and what is our tau w? Tau w is nothing but 2 mu u by delta. And what is delta? Delta is equal to 15 into 2, it will be 30 mu x by u square root of this. So if I substitute this delta over here, I will be getting the value of wall shear stress. Okay, and ultimately I will be getting my skin friction coefficient as 0.73 by Reynolds number x power 1 by 2. All are clear with this idea? So it means from approximate solution of Karman, if we employ the momentum integral equation and parabolic approximation of velocity profile for the laminar boundary flow theory, then I will be getting value of boundary layer thickness as well as the skin friction coefficient. But these values are still called as nothing but the approximate values because we are taking the approximation of the velocity profile. Is this one clear? Now I have explained you the displacement thickness over here. Uh, this is using slightly different method. There on the board I have given you the derivation by using slightly different method by taking the physical inference. But quickly, if you want to see, or okay, we can continue with the same definition whatever I explained you on the board. So we need not to derive it again. Okay, so this formulation I have already given you over the board. So one important point now, if I have calculated displacement thickness, then ultimately I can also, if I have calculated the velocity profile u by u, if I approximated, then I can substitute u by u over here and I can calculate the corresponding formulation of my displacement thickness also. So you can see that displacement thickness will be nothing but 0.334 times of delta for your particular case. Okay, so all are clear with this idea? So displacement thickness formulation I have already discussed, which is integral 0 to delta 1 minus u by u into dy. Now you need to simply substitute the formulation of u by u from the this particular formulation, and then you can calculate delta star by x as nothing but 1.83 by Reynolds number square root. Okay, so you can calculate the corresponding value of the displacement thickness also. Now, till now whatever we studied, that is something which is called as the approximate solution. Okay, Karman's analysis gives us the approximate solution only. But if we have to go for the exact solution, then we need to solve the Navier-Stokes equations. Okay, and while solving the Navier-Stokes equations, we find difficulty that if we can take all the terms of the Navier-Stokes equations for boundary layer flow, then solution is not possible. Okay, so we need to apply certain flow simplifications over here, which will simplify our Navier-Stokes equations, and ultimately by using these simplifications, whatever the boundary layer equations we are getting, we can analytically solve these equations. Okay, so typically whenever we will be analyzing the boundary layer flows, if I talk about simply the flow over a flat plate will be having infinite width. So it means flow can be approximated to two-dimensional situation. For two-dimensional situation, this will be my continuity, x momentum and y momentum equations. Okay. Now we need to apply over here the Prandtl's simplifications, and typically after applying Prandtl simplifications, whatever we are getting, that is called as the Prandtl's boundary layer equations, and the solution of Prandtl boundary layer equations is considered as the exact solution of the boundary layer flows. Okay. So Prandtl's first simplification was, I discussed to you earlier also, let me once again quickly discuss it over here. So Prandtl's first simplification was that boundary layer is thin, so this is delta, and outside boundary layer, if any streamline is there, it is having small displacement. So because of the small displacement, we can say that V velocity in the vertical direction will be very small in comparison to velocity in the horizontal direction. Using this simplification, we can say that, and other simple approximation is that within the boundary layer, whenever you will be plotting different velocity profiles, you will be finding that the nature of velocity profile at different x locations is same. At different x locations, the nature of velocity profile is same, and only major variation you will be finding with y. Typically with y also nature is parabolic only, but the gradient is actually variable. So because of this, you can make few more approximations that all the gradients which are existing in x direction, these will be very small in comparison to the gradients present in the y direction. So that's why I am writing that del u by del x is very small in comparison to del u by del y. Why? Because in x direction, if you see, your length scale is L. In y direction, your length scale is delta. If anything, for calculating gradient, what is the meaning of del u by del x? The meaning of del u by del x is that u velocity divided by length scale in x direction, which is L. The meaning of del u by del y is u velocity divided by length scale in which direction? y direction, which is delta, boundary layer thickness. Okay, and for thin boundary layers, delta is very very small in comparison to L. If delta is very very small in comparison to L, so ultimately my L will be a large number. So some same quantity divided by L and same quantity divided by delta. So one which is divided by delta will be large. So that's why for the thin boundary layer, I can say that del u by del x will be very small in comparison to del u by del y, and similarly del v by del x can also be approximated very small in comparison to del v by del y. Okay, so these three conditions are coming because of the presence of the thin boundary layer. It means delta by L is small. All are clear with this idea? Then we have, if now I apply all these things into my y momentum equation, then from the y momentum equation, this term and this term will be 0, and ultimately I will be getting that del p by del y is nearly equal to 0, which clearly means that pressure is only a function of x. The meaning of this is that if this is my boundary layer, then pressure at any value of x at different points, say y1, y2, y3, everywhere pressure is same. But if I vary points in x direction, then pressure is different. Okay, so that is the meaning. So it means that if I calculate pressure outside boundary layer, then I can apply the same value of pressure within the boundary layer also. Okay, so outside the boundary layer, because flow will be inviscid, so using the Bernoulli's theorem, if I neglect the potential head, then I can write P plus half rho u square is equal to constant. And if I do the derivative of this, then I will be getting del p by del x, which is nothing but equal to dp by dx minus rho u into du by dx. So ultimately, pressure gradient in x direction within the boundary layer can be replaced with minus rho u into du by dx. Okay. And third important point is, because we are finding that the major variation of the velocity is in y direction, so that's why I can say that the second gradient of u velocity with x will be very small in comparison to second derivative of u with y. So this is the final assumption which we will be making. So after taking these assumptions of the thin boundary layer, which particularly were formulated by Prandtl, then we will be getting the simplified set of governing equations. One we will be having continuity equation, other we will be having momentum equation, and in the momentum equation our pressure term is replaced with u into du by dx, and in the last term, if I generalize it to shear stress for turbulent flows also, then shear stress will be simply equal to mu del u by del y for laminar flow, and for turbulent flow it will be mu del u by del y minus rho u dash b dash bar. Okay, so these equations are typically called as Prandtl's boundary layer equations, which Prandtl has given long back in 1904. Okay, and typically these are being used nowadays also for all the types of thin boundary layer flows. Okay, one important point, whenever we are applying these boundary layer equations, we have to consider that these are applicable for Reynolds number greater than 1000, because for Reynolds number less than 1000, this assumption of delta very very small than L is not applicable. Okay, so that's why these are applicable. These equations are applicable only for Reynolds number greater than 1000. Okay, now whenever we have the governing equations, we also need to apply certain boundary conditions, then only we will be able to solve the equations. Okay, so what are the boundary conditions? At y equal to 0, u and v will be equal to 0. One is no slip boundary condition, u equal to 0, and impermeable boundary, v equal to 0. Another simple condition will be applicable, because we have seen that delta we define in such a way so that at this point my velocity reaches nearly equal to 0.99 times of u infinity. So that's why second assumption I can say that at y equal to delta, my u will be equal to free stream velocity, capital U. Okay, and this capital U can be a function of x. All are clear with these boundary conditions? So if I apply these equations, Prandtl's boundary layer equations, and these set of boundary conditions, then I can solve any boundary layer flow. So now let's see the solution of boundary layer flow. So solution of boundary layer flow was first done by Blasius in 1908, and Blasius was once again the student of Prandtl. So whatever equations Prandtl has derived, these were solved by his student Blasius for flat plate flow. Okay, so what Blasius has done, Blasius has used one parameter eta, which is called as a similarity variable. Eta is called as similarity variable. Of course, I will not be giving you the full derivation of Blasius solution over here. I will try to discuss the key highlights of Blasius solution. Particularly, those who have more interest, they can refer to the books of advanced fluid mechanics, such as viscous fluid mechanics by F.M. White, or other books of the advanced fluid mechanics. And if someone is very much interested in the solution of or understanding of boundary layer in more detail, then there is a book by Celesting which is particularly only for boundary layer flows. Okay, so you can refer to that book. So I will only discuss the key highlights. So in case of this laminar flow conditions, what Blasius has done, Blasius assumed one similarity parameter. This was the similarity parameter eta, which is equal to y times capital U by nu x and square root of this. Okay. The idea of this similarity variable is, typically my flow over a flat plate is nothing but a two-dimensional flow. Okay, so here variation will be in x direction as well as in the y direction. But by using this similarity parameter, because you have coupled the y and the x variables into a single parameter which I am calling as eta. So if I use this particular formulation, and using this formulation, if I transform my Prandtl's boundary layer equations, these two equations, if I represent these equations only in terms of eta, okay, so simple derivatives I need to calculate first, del eta by del x, del eta by del y, and then I need to substitute these into nothing but my, then I need to calculate del u by del eta, del v by del eta, and then I need to substitute these into my Prandtl's boundary layer equations, and if I substitute, then I will be getting only a single equation out of all the terms, and this equation is f triple dash, the meaning is f triple dash meaning is del cube d cube f by d eta cube. Why I am saying d now? Because now the equation has converted from partial differential equation to ordinary differential equation, because when we were in the xy coordinate system, then we were having dependence on two parameters x and y, but eta is combining the both dependence into a single similarity parameter. So that's why now my differentials will be nothing but the ordinary differentials. Okay, so f triple dash eta plus half of f into f double dash will be equal to 0. This is the famous equation which is called as Blasius equation. This particular equation is called as Blasius equation. And what is f over here? So to understand f, we can say that the ratio of u by u is nothing but equal to f dash eta. So if I have to understand what is f, so I can understand from this quantity that f dash eta is equal to u by small u by capital U. So it means that my velocity profile is nothing but combined together at all cross sections into a single similarity parameter eta. Okay, and the boundary conditions which were at wall y equal to 0, u equal to v equal to 0. So u is nothing but f dash eta, so that's why f dash 0 equal to 0, and further analysis shows that v is nothing but can be written with f of 0, and at y equal to infinity u has to be u infinity, So that's why f dash infinity will be becoming equal to 1. So these are the boundary conditions. Okay. By applying these boundary conditions, now this equation cannot be once again solved analytically. One has to do numerical integration in order to find the solution of this equation. So if we apply numerical integration or if we do the series solution, then we can construct this table. So in this table, first parameter is eta and second parameter is u by u, and u by u is nothing but f dash eta. So this is the table in between eta and u by u. So you will be finding that corresponding to eta equal to 5, when eta is equal to 5, then your u by u is becoming 0.9915. So what is the meaning of that? When my u by u becomes 0.99, it means that is the point where boundary layer thickness is present. So in order to calculate the boundary layer thickness, I need to equate eta equal to 5. Is this point clear? So this is the definition of eta. I have equated this equal to 5. If I equate this equal to 5, corresponding to this, whatever the value of y I am having, that value I can call as delta. All are clear with this idea? Okay, this is important point. Okay, basically with eta we have seen the variation of u by u, and this variation is becoming 0.99 when value of eta is 5. And once this is 0.99, it means we have the occurrence of the boundary layer thickness. So if you have the occurrence of boundary layer thickness, then y I can replace with delta. Okay, so that's why delta at 99% will be equal to 5. From here, delta by x will be equal to 5 by square root of Reynolds number. What was delta by x from the Karman's momentum integral equation? 5.5 by square root of Reynolds number. This is the exact solution, that was approximate solution. So we can say that Karman's approximate solution was giving us results within the 10% of accuracy limits, because their coefficient was 5.5, here coefficient is 5. Okay, so 0.5 deviation is 10% of the actual coefficient. Is this point clear? So that's why Karman's momentum integral theory was giving us nothing but the 10% accuracy in terms of the exact solution. And if you calculate delta by x, so if you calculate skin friction coefficient, it will be 0.664 by Rex. How much was from the integral equation? 0.73 by Rex. So here also almost 10% deviation is there. Okay, so it means what we are doing, basically whatever the things we derived from the momentum integral equation, same things we are deriving from the exact solution of the boundary layer equations, Navier-Stokes equations. Okay, and if you calculate the displacement thickness, then delta star by x is equal to 1.721 by square root of Rex, and this was equal to 1.83 by square root of Rex. So it means within the limits of approximate 10%, our Karman's solution is actually applicable. Okay, but exact solution is giving us the values over here. So all are clear with this idea? Then, of course, when we do calculate the boundary layer thickness, our interest is also to calculate the wall shear stress. And formulation of wall shear stress will be nothing but Cf times half rho V square. By using that formulation, Cf we have already calculated, and then simplifying, this is the formulation of wall shear stress we are getting. So, two important conclusions we are getting over here. For laminar flow over a flat plate, wall shear stress tau W is inversely proportional to square root of x. wall shear stress is inversely proportional to square root of x. It means that if you make the analogy to your pipe flow, in case of pipe flow, for fully developed laminar flow conditions, the wall shear stress was independent of the length. Wall shear stress was uniform. Okay, is this one clear? In case of laminar flow for ducts, wall shear stress was independent of the length of the duct. Here it is inversely proportional to length of the duct. Second important point, wall shear stress in case of laminar flow was what? It was proportional to u or independent of u? It was proportional to u. Okay. On contrary, here wall shear stress is proportional to u power 1.5. So these are the comparisons which we can make for external flow from the commensurate analogy of internal flow. Okay. So if I have to calculate the drag force, then of course drag force will be B times integral 0 to x tau w into dx. Okay. And from this point, if you calculate, then d of x will comes out to be 0.664 into b rho power 1 by 2, mu power 1 by 2, u 1.5 and x power 1 by 2. Okay, so it means that drag force is proportional to square root of x. So whenever you will be moving along the x over a flat plate in a parabolic fashion, in a power law fashion, your drag force will keep on increasing. Okay, if you increase the length of the plate or move along the length of the plate. Now, one important term is there, which is called as drag coefficient CD. CD is called as drag coefficient. Okay. So if I calculate the drag for the entire plate, drag limit of this x will be from 0 to L. Is this one clear? For entire plate, my limit will be 0 to L. X is up to any arbitrary value of the x. If I have to calculate the drag for entire plate, then it will be 0 to L. If I calculate the drag force for the entire plate, it means d as function of d integration from 0 to L, and then if I write that my drag force is equal to some drag coefficient times half rho u square. Up to this becomes identical to shear stress. If we have to calculate the drag force, then we need to multiply area also. Okay. And what is the area at which shear stress is acting? One is length of the plate and another is normal to the board width of the plate. So B times L. That will be my formulation of drag force if I write it in terms of the drag coefficient. From this I can say that my drag coefficient will be 2 times total drag force over the plate divided by rho u square into Bn. Okay. Now if I substitute the formulation of drag force d of L from this, then I get 1.328 by Reynolds number, and this Reynolds number I am calculating for the entire plate. That's why in its subscript I am writing REL. Is this point clear? This is what? Drag coefficient. And what was skin friction coefficient? Skin friction coefficient was 0.664 by Rex square root. If you multiply it with 2, then it will be becoming 1.328, and in place of x, if you write x equal to L, it means if you calculate skin friction coefficient at the trailing edge of the plate, then you can write it 2 times Cf at N. So it means that drag coefficient for a flat plate under the laminar flow conditions is nothing but equal to 2 times of the skin friction coefficient when it is calculated at the trailing edge of the plate. Is this one clear? All are clear with this idea? Then of course, you can also write drag force from the momentum integral equation, drag coefficient. From momentum integral equation, it will become 2 by L times integral 0 to delta u by u, 1 minus u by u dy. And from here, CD will be becoming 2 times theta by L. Okay. And delta by x is this. So from this formulation, if you calculate H, which is delta star by theta, this is called as flow shape factor. So flow shape factor for laminar flow over a flat plate is nothing but equal to 2.5. Okay. And if the value of flow shape factor increases, then upon increasing the value of this flow shape factor, you will be finding that your flow separation will be occurring. So it means for flow separation not to occur, your shape factor should be small. If shape factor is increasing, then there will be high chances of the flow separation. Okay. So then for turbulent flow, we will discuss in the next class.